contributor to the Neptune project that he will introduce today. He has been doing a lot of research on post-quantum cryptography in that university, zero-knowledge proof systems that we have been looking into today briefly in the presentation in the morning, and also probable security for public key crypto systems. And this is why he was member of Chain Security, that is one of the largest auditing field firms in the space, actually. So we're really thankful to have you, Alan, here today. Thank you very much.
Thank you. Let me correct one thing. I was not a member of Chain Security. That was Fabiola.
Really? But we only met
then.
We met at Chain Security.
At that point,
they were
okay.
hosting seminars, not too dissimilar from this seminar, and I thought, I'm new in Switzerland anyway, why don't I go there? And that's how we met. Okay. So what you're about to witness was designed to be a 2.5-minute pitch. But unfortunately, I've forgotten my script. So I'll be looking for my words as I deliver the presentation, and I'm afraid I won't be able to make it back under 2.5 minutes. So Neptune is a post-quantum, scalable, and private layer 1. Cryptocurrencies have gone from 0 to more than $1 trillion in less than 14 years. And if you're here, you know that there's a lot more potential in the future. But transparent ledgers like Bitcoin are terrible for privacy. And existing privacy solutions like Zcash and Monero don't scale. And layer 2 privacy solutions like Aztec or ZK Sync, they inherit the security vulnerabilities of their base layers. And all of the solutions I just mentioned rely on quantumly insecure signature schemes, which means that if a quantum computer is built large enough, it will crack your public keys like twigs. Neptune is the solution. It marries post-quantum security with privacy and with scalability, and the way it does this is by integrating ZK Starks into the consensus logic on layer 1, where they belong. ZK snarks are already known for their capacity to generate privacy as well as scalability. ZK Starks is the next evolution of the same line of technology that also gives you post-quantum security. This slide is a little outdated. So we already have a Stark engine. We don't have recursion yet. We do have a blockchain node, and we just launched testnet earlier today. But we don't have recursion yet, so that merger that you see on the slide will happen at some later stage. Between my founder and me, who's sitting here, by the way, we've co-authored several influential papers in the field of cryptography as it relates to blockchains, and built financial blockchain-based infrastructure securing more than $3 billion to date. We're trying to follow the template of Bitcoin's launch as closely as possible, which means we're keeping the pre-mine as small as possible, subject to being able to hire the team required to launch. And we also are trying to follow Bitcoin's model for governments as closely as possible. Satoshi obviously disappeared, and while we can't disappear because that would make the investors uncomfortable, we can make the company dissolve. So at the point of dissolution, no one will be in control of money. So ask yourself what the future global financial infrastructure needs to look like after the adversaries activate their quantum computers. Thank you.
Thank you very much. Thank you very much, Alan. I have a question before someone jumps in, but because it is fascinating because you are doing something that is, I am very interested in cryptoeconomics, and you are doing something that you are breaking the mold that was created by Ethereum in 2014, that is basically that the amount of tokens that are pre-allocated to investors or the development team is a very sizable part of the pie. So, in general, investors have a high incentive to participate in these systems exactly because they are getting a large part of the pie, part of the thing. So they can de-risk themselves very early in the process. How easy is it or not, or how, let's say, out of your experience trying to build it in this very novel way now after 14 years, even if it should be old, this system. Is it doable? Do you think is reachable? Are you close to your target? Now you are close to set, you already sent the testnet, but reaching into production. Is it working out, this way of attracting the financing?
We are still fundraising, and we are running a very tight budget, and I would go so far as to say too tight, but fortunately we make up with that for resolve, and we make up for that with resolve and determination and ideological.
Yeah, fantastic. Yeah, because I think this is exactly how one of the first platforms were developed. That's why it's very interesting as an approach. Your question, please.
Yes. I will speak for myself when I say I have no idea what ZK snarks or starks are. If you could please elaborate on that.
A conventional computer program takes an input and produces an output. But using interactive proofs, which is a branch of cryptography, you can transform that computer program into two computer programs called the prover and the verifier. The prover does almost the same thing, except in addition to producing the output, it produces a proof. And the verifier just looks at the input, the output, and the proof. And if the verifier says it checks out, then you know for sure that the prover actually behaved honestly and ran the program correctly. The nice thing is that the verifier has a time complexity that is far, far, far smaller than naively re-executing the program. So you can verify cheaply. That's where scalability comes from. Mm-hmm. Furthermore, the verifier can verify the proof without access to secrets that are necessary to run the program. That's called zero knowledge. So the verifier can still get certainty about what's claimed without access to the secrets. That's where you get privacy from.
Thank you very much for the explanation, Simon.
So you mentioned once there are quantum computers big enough, does that mean that right now with the one at ETH, for example, you wouldn't be able to crack the crypto functions we have right now?
To my best knowledge, currently the existing quantum computers are not big enough yet. But if I were in possession of a big enough quantum computer, I would not advertise this.
Yasir, and then go with you.
So, as a computer engineer, what kind of mathematics should I study to really understand the mathematical principles behind stars? Like, to really understand it in depth? Could you explain?
Start with discrete algebra, and then move on to coding theory. We use a lot of coding theory. Discrete algebra and coding theory, you can understand the mechanics. If you want to make the next step and understand why it's secure, then you also need probability theory.
Is that it, would you say? Is that it? Or is there anything more?
All of these things touch various related fields, right? So once you study discrete algebra, you'll learn about rings and elliptic curves, and It's a rabbit hole, but you want to make sure that you start jumping into the right rabbit hole.
What about cryptography?
Absolutely necessary. I was trying to deconstruct it into simpler terms, but I'd say cryptography lies somewhere in the intersection of those three fields.
Yeah.
Thank you so much.
Your question.
My question is it worthy to protect the security in the post-quantum era? Because I learned a little quantum physics, and even the quantum computer is very fast. It needs more energy to get a result because it needs many times computing to get one result because the probability. So I think protecting security is not so worthy.
So if I understand your criticism correctly, the quantum computers will take too much energy to break crypto.
Yes.
This is the first time I've heard that claim. I'm not a physicist, I'm a cryptographer, and I wonder why is there a whole branch of cryptography devoted to protecting information in the presence of quantum attacks. I would wonder, how does this energy requirement scale with the duration of the algorithm or with the number of qubits used? Because that might undermine your argument. If the energy consumption is huge for a long algorithm, maybe it's not so huge for an algorithm that doesn't take so long to run. And certainly for attacking the discrete logarithm problem, whether over finite fields or elliptic curves, the algorithm has a very good running time.
Okay. Is there any final question or two? Well, please go ahead.
It's not a technical question, but as an early stage founder, what are some of the challenges you faced and how have you overcome them?
I think the biggest challenge is to quit being an engineer and start being a business person. As a founder, you need to raise money, you need to understand contracts, you need to hire people, and we can do this because we're so much in love with the engineering task. But just because you're a good engineer doesn't mean that you're good at all the other things, and you have to learn a lot about that. I'd say that's the biggest challenge looking back.
The final question.
What is the difference between StarkNet?
StarkNet is a layer 2. They are using the same technology, but they are based on Ethereum. So if you want to get your money out of StarkNet, you withdraw to layer 1 on Ethereum, where quantum computers can crack your codes.
Okay,
Thank you very much. Thank you very much, Alan.